Hello class, in this video we shall be discussing on the topic vapor pressure of liquid solutions. So liquid solutions are formed when the solvent is liquid and the solute can either be gas, liquid or solid. Okay, we shall be discussing on two types. Okay, that is when the solute is liquid and when the solute is solid. So the first one is when both the solute as well as the solvent are liquid. Okay, so that is vapor pressure of liquid solution. Here, according to Raoul's law, it states that at a given temperature for a solution of volatile liquids, the partial vapor pressure of each component in solution is equal to the product of the vapor pressure of the pure component and its mole fraction. Let us consider a binary solution of two volatile liquids, say A and B component, okay, having the mole fraction XA and XB respectively, okay. If PA and PB are the partial vapor pressure of the components in this solution, then according to Raoul's law, we can write PA is equal to PA degree into XA, okay, their products, okay. So PB also can be written as PB degree into XB, where the PA degree and PB degrees, okay, are the vapor pressure of the pure components of A and B respectively. Now, according to Dalton's law of partial pressure, the total pressure will be the sum of the partial pressure of the components of the solution. So this is given by P equals to PA plus PB, and we know PA is PA degree X of A plus PB is PB degree of X of B. Okay, again from mole fraction we know that the total sum of the mole fraction will be equal to 1. Okay, so we can also write in this way, XA will be equal to, by transferring this XB to the right side, it will become 1 minus XB. So instead of XA we can replace it by 1 minus XB. So P will be equal to P of A degree, okay, 1 minus XB, which is, okay, like this, and then plus PB degree of XB. Again P will be equal to PA degree minus PA degree XB plus PB degree XB. Okay, this is how we get. Again, this one also can be done like this, that is P equals to PA degree, minus sign you can take out common, okay, and PA degree minus PB degree, and XB also taken out common, but I have written on the right side. Okay, so this is how we can do. Now, as you can see here, okay, we can express the partial pressure, okay, the total pressure can be expressed in the form of this, where we can take any one of the mole fraction, okay, instead of taking both the mole fractions, we can also express in the term of, or in the form of, single mole fraction. Let's now try to understand the graph of the vapor pressure of liquid solution. Okay, as you can see, the equation here, it is of the linear function, which means it will give a straight line. Okay, now on the graph, the horizontal axis is of the mole fraction, the vertical axis is of the vapor pressure. Okay, now on the horizontal axis, see, there are two cases, okay, two parts. One is when the solution contains only the component A, okay, that's why component A is 1 and component B is 0. So it says that the component B is absent and only component A is present. And on the right side, X of A equals to 0 and X of B equals to 1, which means the component B is present and component A is absent in this solution. Okay, so as you can see here, when X of A equals to 1, we get P of A equals to PA degree, which means when only, okay, component A is present in the solution, then the partial pressure of the component A will be equal to the vapor pressure of the pure component A. So the vapor pressure of the pure component A, suppose it is up to this value, okay, so we get point here. And when x of a equals to 0, we get p of a equals to 0. So x of a 0 means when the component A is absent and only component B is present. So the point comes here. So we join these two lines. Similar case for this second component, that is of B. You see here, when x of B, or when only the component B is present in the solution, that time we get the partial pressure equivalent to the, or the partial pressure is equal to the vapor pressure of the pure component B. So we get a point here. And then when x of B is equal to 0, that means the component B is absent and only component A is present in the solution. So that time we will get P of B equals to 0. So that means at this point, okay, this is a point. So we join these two lines. Now finally the total vapor pressure will be the sum of the component A, okay, the partial pressure of component A as well as the component B. Okay, now as you can see on the graph, we can, okay, we join the points of PA degree and PB degree. Okay, so this is the minimum value of the pressure when they are in solution, okay, when they're both mixed together, and this is the maximum pressure, okay, in solution. So we join these two lines, okay, we join these 2 points, okay, not line but these 2 points, and hence we will get the total vapor pressure. By this we can say that the total vapor pressure is between the value of this one and this one. Say suppose this one is something like 2 atm, okay, and that one is 10 atm. So the total vapor pressure will be between these two, okay. So that is what it means. Let us now take the next one, that is vapor pressure of solution of solid in liquid. Let us take, okay, the solute to be non-volatile solute. So non-volatile means they do not form vapor, okay. So now when we mix the non-volatile solute with a volatile solvent, then during evaporation the vapors are formed only from the volatile solvent, okay, and they escape into the vapor phase. So therefore the vapor pressure of the solution will be decreased, or will be lesser than the vapor pressure of the pure solvent. So let us see with an example. So this is a pure solvent and this is the mixture of solvent as well as the non-volatile solute, okay. Now since evaporation is a surface phenomenon and the vapor pressure depends upon the number of molecules that escape into the vapor phase, okay. So now in case of pure solvent, during evaporation, see, all the spaces are occupied by the volatile solvent, so all the molecules, okay, on the surface will escape into the vapor phase. But in this case, when a non-volatile solute is mixed with the volatile solvent, what happens? Some of the surfaces are also occupied by the non-volatile solute. So what happens? There will be a lesser number of solvent molecules escaping into the vapor phase. So since it has less number of solvent molecules, therefore the vapor pressure will decrease, okay. Now let us see this one, that is here, the first part, okay, that is this one. So if, okay, we have two components, one is of the volatile solvent, the other one is of the non-volatile solute, okay. So for the volatile solvent, okay, for the volatile solvent we can write Pa equals to Pa into Xa according to Raoul's law, okay. But then for the solute, okay, for the non-volatile solute, the pressure, okay, the vapor pressure of the solute will be equal to 0, because although the number of moles is not equal to 0, but then the pressure due to the non-volatile solute will be 0. So therefore the total pressure, okay, here Pb will be equal to 0. So total pressure, okay, total pressure will be Pa plus Pb, okay, but Pb is 0, so therefore we get only this one, okay. So we can write P equals to P of A, which is equal to PA degree into X of A. Hence, we can also state in this way for a non-volatile solute. Okay, Raoul's law states that at a given temperature, the vapor pressure of a solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. Okay, so the pressure, okay, the total vapor pressure of the solution will be directly proportional to the mole fraction of the solvent. Okay, so here we did not mention this, we did not mention product of like that. Okay, so because this is the constant value, therefore we did not mention that way. Okay.